for yesterday is that arcs produce strong plasma jets driven by these electromagnetic forces, and those jets will depress the surface of the weld pool, controlling some of the surface depression. They influence the arc stiffness, the arc stability, and the location of metal vapors. Oh, and drop and transfer. That's how, if you have a consumable electrode, the drops come off the end of the electrode, and these jets, you're basically, these drops are transferring in the plasma. In fact, it's the plasma jets that allow you to weld overhead. You ever thought about that? How can you weld overhead? Why do the drops go up? They go up if they're small enough drops and you have strong enough wind, it'll blow them up. You have to have a small enough weld pool that it doesn't fall down, but surface tension will hold it in as long as you're something where surface tension and gravity are at least comparable. You can hold things in by surface tension. And we know that for metals that's around 3 millimeters as a characteristic distance. So if I have a fairly thin weld pool and I have a relatively strong plasma jet, I can weld overhead and the drops will go up and the pool will stay there. Now, another thing, when I talk about surface depression, if you're welding pipe, you might start out with a joint design that looks like this, and you've got to penetrate through here, and since it's pipe, and you've got some center line through here, you can't get to the inside to do anything. So typically on a pipeline like the Alaska pipeline or something, the root pass will be put in with a stick electrode of a different type than the fill pass is up above. And the reason is that root pass electrode is one that will have a strong plasma jet, and it will essentially punch a hole through here, and you pull that hole through there, and the metal comes around behind, and you get a nice underbead down here, because you're doing what we call keyhole type of welding. Okay? You drill a little keyhole, and you push things along. Okay? And the metal swirls around behind, and you get a nice underbead. If you just try to melt from the top, there's variations in the melting rate, and sometimes you'll melt all the way through. Sometimes you melt too far through and it drops through, and then you got a defect you have to repair. And then sometimes you won't get full fusion and you'll have a lack of root fusion, which you pick up on x-rays or whatever. So there's lots of different types of defects. Yeah?
When you do the simple weld, then you don't have to back gouge the other side of it then? Is that...
No, this is a pipe weld, so I can't get to the inside. I'm not going to back gouge. Yes, you can back gouge. So you're trying to do something where I can get a good inside surface to that inside the pipe. You get a good inside surface because I can't get in there to back gouge. Ordinarily, if I'm doing a two-sided heavy plate weld, yeah, I flip the plate over and I back gouge and get rid of all those root defects, because typically you will get a lot of root defects in a welding process.
Isn't there some type of pipe welding where you put an insert in there that...
Yeah, it's called an EV insert for electric boat.
Yeah.
Okay, and the EV insert is just a piece of wire, and they roll it so it looks nail-shaped, kind of. Okay, you put that little insert ring in there for the pipe, and now you go in with typically a gas tungsten arc and just melt the whole thing. And hopefully, if you do it right, the head of this nail, upside down nail, it's a wire that's rolled to that shape, right, cross section. So it's not a nail. But, if you do it right, you'll get a beautiful bottom root fusion with gas tungsten arc, non-consumable for the root pass. That problem is that's very expensive, and each one of those little rings costs an extra $1. It's actually not that expensive, but actually only costs you a couple bucks. But not, it's really only really high quality welding, such as submarine construction piping, that people worry about that. Okay, it's called an EV insert for electric boat. More typically on a pipeline, people have learned to do this kind of keyhole welding, where you have a very strong plasma jet, drills a little hole, and now you're carrying a air hole right along there, and as the metal flows around behind, you get good fill in and surface tension. Because now I've got liquid metal layers that are millimeter thick, and surface tension is going to control that jet, the shape of that. Whereas if I just melt the whole thing, I'm going to have a distance of 4 or 5 millimeters maybe, and the whole thing can drop through by gravity. So by doing keyhole weld, you basically are using surface tension to your advantage to get a uniform bead shape. Actually, there's I think, an excellent quality control technique in pipeline welding. Anybody know what it is?
Fill it up.
Right, fill it up. When you go out on a pipeline job, first of all, 98% of the pipeline welding in the world is done by a union in Tulsa, Oklahoma. Okay, they basically control pipeline welding in the world. Mostly because the U.S. oil companies kind of control the pipeline welding, and these guys, that union has kind of a stranglehold. In fact, when they built the Alaska pipeline, they had automatic welding machines that could have welded the pipeline about twice as fast. But the union said, if you bring those on the job, it'll never be built. It's basically extortion, okay? But I mean, it was true. If the union didn't want it built, they could have found other ways to screw up the whole project. So they manually welded the Alaska pipeline. Now it turns out, in the last 25 years, they have brought in some of these automatic machines. And the automatic machines don't use inserts, they're gas tungsten arc welds for the root pass, and then the fill passes are gas metal arc. And because gas metal arc is more efficient, they can pay for themselves. However, the quality control technique they use on the manual welding of pipelines is with most of these pipelines, if you got a gas pipeline that lets go, you got a huge fire and expensive loss. I mean, you could be moving on an oil pipeline, the Alaska pipeline, you're moving at peak 2.25 million barrels a day down that pipeline. And if that was $15 a barrel, you're talking about $35 million worth of product every day. And if that pipeline went down for a month, you're talking $1 billion loss of sales. So the oil companies have a vested interest in trying to keep the pipelines, whether it's oil or gas, operating and not have failures. So they do 100% inspection and radiographic inspection of the welds. And if the welder produces a defective weld that has to be repaired, he repairs it off the clock on his own time. So there is an incentive, okay? You still have to meet your production quotas. You have, you basically, if you're working 12-hour days, you got to go out and work an extra 4 hours one day to repair your garbage, your own garbage. So that's one of the deals got with the union. The other thing about that union, doesn't matter whether they're putting a pipeline in Bahrain or wherever, they require them to fly in American food. And they found that in the long run, it turns out flying in, meat and potatoes or whatever is more efficient, because otherwise you got the welders all out there from Oklahoma who are going to get sick on the local food, or they're not going to like it and they won't eat it, and so then their productivity goes down. But it turns out to be cost effective and it's written into the contracts that the food will be American food, and they basically, air freight it in from the United States, so they get to eat normal food. What's normal for them, anyway? Which I guess is McDonald's. Any other questions? One other thing I want to point out: if you want to get a stiffer arc, just like we had pre-mixed flames and we had jet burners, there is an equivalent to a jet burner called a plasma arc. And you saw a plasma arc cutting torch. A plasma arc essentially has can be either water-cooled or non-water-cooled, but for high currents, it's going to be water-cooled. But it has a copper chamber, water-cooled or air-cooled. It has a tungsten electrode, and the tungsten electrode actually strikes an arc inside this constant volume chamber. And just like for a jet burner, if you do all your expansion at constant volume, you get a tremendous jets shooting out. And so you get a very, very stiff arc for a plasma arc. This is just if a gas tungsten arc with a tungsten electrode is just sitting there in the air. It makes a nice bell shape as it expands and flows. If you do the same thing in a constant volume surrounded by this copper cup, and you let the arc shoot straight through, then you can get a very high velocity and a higher heat intensity. And so plasma arc is often used for welding things like aluminum and copper, because you want 20,000 watts per square centimeter rather than 10,000, because you get this very high velocity. You also get a very stiff arc. You also get this keyhole welding technique, where you blow through and you carry this hole, this gaseous hole, through a flat hole. So it's kind of the line heat source that I talked about yesterday. Plasma arc is used, for example, in welding of the space shuttle main tanks. They use variable polarity plasma arc on these aluminum alloys, and they use keyhole welding. And if you get plasma arc set up right, you can weld 3/8 of an inch in one pass. The problem with plasma arc is you obviously have some very extreme conditions for your copper and your tungsten, and the distances here may only be a few millimeters, 4 or 5 millimeters in some cases, or a couple of millimeters in that direction. And so you get erosion over time, and typically everything has to be replaced about every half hour, which means you're shutting down and replacing your tips and your cups, and your copper cups and things like that. Turns out the way plasma arc was discovered was a guy named Bob Gage at the Speedway Labs at Union Carbide in Indianapolis, Indiana, was doing fundamental studies in the 1950s of gas tungsten arcs. And so he was basically striking the arc on a copper plate so he could do some studies of the arc. And for whatever reason, he drilled a hole in the copper plate and ran the arc over it, and he saw this jet shooting through the hole. Jet of hot plasma. So I don't know if they showed you when they showed you plasma cutting before. It actually is a little flame, and you can turn it on, and you can have the flame right there. And if you want, you can pass just like you can pass your hand through a candle. You do it a little quicker with a plasma arc because it's a little hotter than a candle. But nonetheless, you can, in that pilot flame, you can pass your hand right across the plasma. Okay? You don't like that? You don't usually electrocute yourself. Okay. Although, in general, plasma arc cutting equipment has 400 open circuit volts and is a pretty good thing to electrocute yourself. Pass around the sign up. I had crossed off a couple of days earlier this week, so just sign up for today. It's mostly just to keep track of who's here and whatnot. Make sure I know who's actually on the rolls. Any other questions on those things? Let's go through heat flow now. We talked about the Rosenthal solution, and I may come back and throw up some of those overheads again, but right now I want to talk about the Fourier number. Which is a dimensionless number. X is the square root of alpha T, where alpha is the thermal diffusivity. I'm going to go, well, actually, I might as well go through it right now. Alpha is equal to the thermal conductivity divided by rho CCP. So, if you look at the diffusion equation, Fourier's first law just says that the heat Q is minus K dT/dx if I do it in one dimension. And the second law is d squared T dt squared is equal to alpha d squared T dx squared. And that says, all that says, this is, second law is derived from the first law. Basically the first, well, I'm sure how that's done. Anybody remember how that's done? If I have heat flowing into some solid body, I just take a little volume element, and if I have some temperature profile across this volume element, Fourier's first law says that the rate of heat flux Qn to this little volume element is equal to the gradient times the thermal conductivity. The heat out is also the gradient times the thermal conductivity, K minus K dTdx. If I want to know how fast the heat accumulates, I need to know rho C sub P, the heat capacity of this thing, times the difference between these two, right? The heat either accumulates, in this case it'll accumulate, it actually, well, I'll ask you, will it accumulate here or not? Which one's larger? Q in or Q out? Q in is larger, so the heat accumulates and this thing heats up. So it turns out, if you write down Q in minus Q out is equal to rho C sub P times the volume of this little delta X, you end up deriving Fick's second law. So there's nothing new to Fick's second law other than geometry, and that you're looking at it turns out now, a non-steady state process. You're looking at the rate at which heat comes in and the rate at which heat goes out. That's what gives you your time. Your X comes from the width of the volume element, which is a dx. Okay? You can prove it to yourself later. But it turns out that if the curvature is if the curvature is curved up this way, heat's going to accumulate. If the curvature is the other way, the thing's going to lose heat, right? Because Q out will be larger. So basically, it says the rate of temperature change is proportional to the curvature, because the second derivative of the temperature with respect to distance is the curvature of the temperature, right? If it's a straight line, it's 0, right? And there is no change. Q in is equal to Q out. So, see, the problem is they usually don't tell you the physics or the, how to figure the intuition out of these things. I took 4 or 5 heat transfer courses at MIT. No one ever bothered teaching that. You had to figure it out for yourself. Pick it up off the street. Okay. So the Fourier number, actually, I was going to come over here and talk about the different values of alpha originally. So for alpha for steel, turns out alpha has units of centimeters squared per second, and for steel alpha is 0.1. For copper, it's 1.0. For aluminum, it's 0.6. For stainless steel, it's 0.05. For titanium, it's also 0.05. For nickel alloys, it's typically 0.05. It turns out the thermal diffusivity in most metals does not vary by more than 1.5 orders of magnitude. From the most conductive metal, copper, to the least conductive metal. It turns out copper is not the most conductive metal. Anybody have an idea what the most conductive metal is? Gold, yes. Has about 1.2. And silver has about 1.1. Platinum is actually lower. Okay, lower. I don't remember what platinum is, but it might be 0.8 or something like that. I have to go look it up. In fact, the only table I know of thermal diffusivities is volume 6 of the Metals Handbook in the very first couple of pages. I may have given you that handout, and that's because I wrote that thing. Okay, because I'm always sitting there. What's the thermal conductivity of this or that? So I one time had a student go through it, calculate it for me, and made the tables and put it in the handbook. But in general, if you go to most places, they'll give you thermal conductivity, density, and heat capacity, and then you got to calculate it out. And it's much easier to just know these types of things. Anyway, if the Fourier number, which is the distance that heat travels divided by the square root of thermal conductivity times time, well, you can tell it's a dimensionless number. If that's centimeters, this is centimeters squared per second times time, which is the square root of centimeters squared, which is centimeters. Okay, everything drops out. So it's dimensionless. If the Fourier number is 0.1 or 1 or 10, I'm going to have this is not a little volume element, this is basically a plot of the temperature. This is temperature versus distance plot. If I have a surface heat source and I bring the surface to some constant temperature, I will have an error function solution. Oops. So that's not the one I wanted to draw. Sorry. That would have been fine for 1.0. I will have an error function solution that looks like this. So if I have some, we'll just call it some unit distance x, and this says that the distance x is much less than, oops, I got these backwards. Have I got these backwards? This is 10. Sorry, this is 10. No wonder I had it marked off wrong in my notes. Okay, and this is a 10. Okay. If it's 1.0, I'm going to have an error function solution that looks like this, and it will decrease to about 1/10 when the Fourier number is 1, which is this distance. And if I come over here, I'm going to have something that essentially the solid will be saturated with heat at that point. Okay? Just correct the notes. Okay. So here I have something that is thick with respect to the time that heat's flowing, and in here I have something that's thin. And essentially the heat has plenty of time to flow through the body because it's relatively thin, compared to the time and the thermal conductivity of the material, which are the only three parameters in the Fourier number, right? So you have three conditions. Essentially very thick, very thin, or somewhere in between in the transition region. And so now if I want to, rather than solving Fourier's second law of heat conduction for any thermal problem, I can estimate the size of a heat affected zone or the amount of cooling that occurs in the process. And actually about 2 or 3 of your homework problems ask you to either do this for the Fourier number or the Einstein number, which is d or x over the square root of dt for mass diffusion. If you're where d is the mass diffusivity of the element going through something else in centimeters squared per second. Okay, so it's the same mathematics, the same diffusion equation for mass flow out of Fick's law. It turns out that the diffusion equation is called Fick's first law, and Fick's second law is just the diffusion equation, but you have d in there rather than alpha, and you have concentration rather than temperature. The Fourier number is x over alpha t. This is called the Einstein number because Albert Einstein actually was one of the first people to actually write it down. But it comes out of the diffusion equation, and so you have maybe 3 out of your 10 homework problems asking you to either use the Einstein number or the Fourier number to solve something. For example, one of the homework problems asks if I've got a resistant spot welding electrode, and this is a water-cooled copper electrode, and I've got a sheet of steel down here, or aluminum, and I got another electrode underneath it, and I'm going to pass a lot of current through this thing for a 1/10 of a second, let's say. Okay, 1/10 of a second. We usually in spot welding talk about cycles of current. We got 60 cycles, 60 hertz current. So a 1/10 of a second is 6 cycles of current. Well, if I want to know, well, let's say this is 5. Well, let's just call it 1 centimeter. Okay. I think I may be doing one of your homework problems. This is water cooling up here, and I want to know if by doing water cooling up here, I can influence the temperature of this interface where the heat is generated. You saw some videos that show heat generated and resistance of these interfaces here. So I want to actually generate heat here. I don't want to generate it here because I don't want to wear out my electrodes. So will that water be effective at cooling copper 1 centimeter thick in a 1/10 of a second? That's one of your homework problems. I can tell you right now the answer is no. Okay? You can go through it yourself. Square root of 1 times 1 is 1. the distance the heat travels in 1 second, okay? It would take 1 second to get to this type of temperature profile, and I've only got 1/10 of a second. So this is essentially infinitely thick compared to the welding time of 1/10 of a second. If I was talking about, well, in the automotive industry, they make 20 spot welds per minute. So I got 3 seconds between each one. Will I actually end up, after I separate these things, will that water cooling actually help cool the surface here before it goes and makes the next weld? Well, if you look at this, I'm kind of somewhere between this and this. So I will get some cooling, but I won't get too much cooling. And in fact, we've run experiments. It shows that it takes 15 or 20 seconds to get to some sort of thermal equilibrium when you start doing that rapid spot welding. And as a result, the first few welds you make have different heat transfer characteristics. Those first 5 welds you make in the first 15 seconds will have different heat transfer characteristics than the ones you make after 15 seconds. And all you have to do, you don't have to go through a supercomputer doing a full heat transfer analysis. You can do this back of the envelope calculation just by doing the Fourier number.
I have a question. Actually, I have 2 questions. So when is the Fourier number shortcut applicable?
It's applicable when you want to know, am I just superficially heating or am I saturated? When you really want to know something precise, if you run the Fourier number and it's anywhere close to 1, let's say it's 1/2 or it's 2, you actually have to usually go ahead and now solve the whole problem if you really want to know some details. But in most cases, 95% of the time, all you want to know is, did I saturate my material with heat or did I not saturate my material with heat? The typical type of solution or problem I do to illustrate this for students is, what's the heat affected zone size in a given material? Well, the heat affected zone size is kind of somewhere where the Fourier number is equal to 1, okay, where I've heated the thing up to some distance. If this is X and I heat it up to some intermediate temperature about halfway in between, well, that's when, if you want, the Fourier number is 1/2, if you will, if you want to use 1/2. But just in general, if I take steel and I've got a weld pool and I look at how fast it's traveling along, it's making welds back here, right? And I look at the length of that weld pool, let's say it's 1 centimeter, and let's say that I'm going, it's a fairly fast weld, I'm going to go 10 centimeters per second. That's a fairly fast weld. That's way too fast. Let's do 1 centimeter per second. I can work with numbers like 1. I can divide them, multiply them, square roots, cube roots, all those. So it turns out the time from the front to the back of the weld pool, where I have a heat source that's pumping heat into my base material, is 1 second, right? So X is square root of alpha T, and T is 1 second. If I'm talking steel, that means X is on the order of 3 millimeters. It's 0.031 centimeters, with 3.1 millimeters. Okay, square root of the 10th. Okay, so is that about the width of the heat affected zone? If I had that piece of HY80, you pass it around, yeah, it's about 1/8 of an inch. Is that little heat affected zone you saw in the HY80? It's about 1/8 of an inch in size. I just calculated it, order of magnitude. Now, if I was in copper, this is 1, this is 1, and so my heat affected zone size in copper is a full centimeter. So in copper, now you can see why I need higher heat intensities in copper to do welding on copper, because I'm really preheating a lot of base material in order to get fusion in the copper itself. Okay. Now let's change this problem and say that I am going with an electron beam weld at well, let's just do 10 centimeters per second. Okay. That means this is now, this is still a tenth for steel. This is now a tenth of a second. And so this becomes 1 millimeter. So in principle, in a laser weld, I might get something down, I might be able to narrow the heat affected zone down to 1/10 of its original size. However, not a tenth, but a third of its original size. If I go 10 times as fast, a simple heat flow analysis would say that I'll get 1/3 the heat affected zone size. However, that's not always true. These are the isotherms that can come out of the point heat source, the Rosenthal solution we talked about last time. And this was all put into dimensionless form by Niels Christensen, I mentioned, who was this Norwegian freedom fighter. Niels came here on a Fulbright scholarship after World War II, worked in the basement of Building 8 on his thesis, which was on welding fluxes. It turns out he was already turned his thesis in about 1948, and back then we didn't have computers to store all your data and stuff. He had a notebook, and someone stole the notebook. And Niels thought that, or they thought that it was basically a Soviet spy who was running around MIT. They never did find the notebook. He had to stay an extra year and a half, redo all his experiments before he could graduate. He went back to Norway, became a professor at Trondheim University, which is the big technical university in Norway. And in the mid-60s, under a grant from the US Army, because even in the early mid-60s, the European scientific establishment wasn't very well established. He got a grant from the European Research Office of the US Army, and he also broke his leg or something. He was basically in bed for about 6 months. And while he was in bed, he basically took a Rosenthal solution and he put it all in dimensionless form. And you have a copy of the paper, which is temperature distributions in welding for the British Welding Journal in the mid-60s. Actually, I'm sorry, he actually did this work in the mid-50s, but it didn't finally get published. But it was one of the best paper awards back in the 60s for the metallurgical, in the welding literature. Anyway, so here's a very slow-moving heat source, and if this center circle is in fact the weld pool, let's say that's the fusion line, you can see this little dot dash line here is the locus of the maximum travel, the maximum isotherms, the maximum distance they move out. So here, if I were to look out in the y direction on this one, which is moving faster, and this little dashed line is the locus of where these things, these distorted ellipses reach their maximum y extent, plus y and minus y. So this is you can think of it as a wave behind a boat or something, is the way Niels used to describe it, spreading out. It's basically diffusing out. In fact, it is a parabola, as far as that goes. It's diffusing out as square root of t. Here, if you look at the heat affected zone, the maximum growth, if let's say I go, this first circle is the fusion zone, and going two isotherms out is the heat affected zone. I'm going to define that coming up to that temperature as the heat affected zone. You can see that the heat affected zone grows to its maximum extent when the weld pool is still present. And that basically says the heat affected zone is growing on the heating cycle when the weld pool is still present as a heat source heating up the surface. If I go over here, this little circle right here, I see that if I go 2 isotherms out, I'm way over here, and this is way behind the weld pool. The maximum extent, the weld pool has already gone past. You know, the cows are out of the barn, okay? So the heat source is no longer diffusing things out. What's happening is the maximum heat approach in the y direction, plus y or minus y, is after the weld pool is passed. This is on the cooling part of the cycle. And so it turns out that for something like this, a very fast weld, like laser electron beam, it's the cooling part of the cycle that controls the width of the heat affected zone. On a slow weld, like electroslag or oxyacetylene welds, it's the heating part of the cycle that controls the heat affected zone. When I get in here, I'm getting into kind of a transition ambiguous region in these two, and this is basically arc welding. So in arc welding, I can actually change the size of my heat effective zone by changing the travel speed, or well, basically changing the travel speed or the heat source intensity. Either one of those has the potential to change the size of the heat effective zone. In laser and electron beam, the heat effective zone size is controlled by the cooling rate, and the cooling rate is controlled by the width of the fusion zone. If I have a big broad fusion zone because I have a very powerful but defocused beam, I'm going to get a big heat effective zone. It turns out in laser and electron beam, the heat effective zone size in steels is about equal to the fusion zone width. So if I have a 1 centimeter wide weld and a great big plate, I'm going to have a 1 centimeter wide heat effective zone. That can be bigger than the heat effective zone I get in an arc weld, if I have a really heavy electron beam weld. If I go to oxyacetylene welding or electroslag welding, the heat effective zone size is controlled by the travel speed alone. And the faster I go, the smaller the heat effective zone. So you can use it for things like that, okay? Now you also asked this question of when does the Fourier number work, okay? When can you use it? There's another thing you have to worry about with the Fourier number, and that's whether you have convergent or divergent. This really was for a planar solid. So if I'm talking about heat on, this is a solid material, and I apply heat to the surface, to this surface, and I watch the temperature gradient as the heat goes in there, I can also have divergent heat flow. I can have divergent heat flow where I'm applying heat to a curved surface and the heat has to flow out that way. Well, obviously that's not going to heat things as rapidly. My gradients are going to be smaller, right? I can have convergent, where if I'm heating a surface like this, but all the heat's converging, I'm going to raise the temperature more rapidly. So if I'm looking at convergent, or divergent, I'm going to have something so this is, and this is divergent, and this is planar. Okay, so this is, now, anybody know what types of solutions you get in a cylindrical part? If I have heat flowing, let's say I've got a tube and I got heat flowing out of the tube into the solid body. So I'm heating the inside of the tube and it's flowing to the external surface. That's divergent heat flow. Or I could heat the outside of the tube or a cylinder and it could flow towards the center. And mathematically, what's the solution to the, what type of functions? You get an error function if you do the planar solution. You might know what type of stuff, what is it? You get a Bessel function. Isn't that great? Hey, okay, so I took the course over the math department and taught me how you do Bessel functions, and I can look up in tables of Bessel function of order 0 and order 2 and all that stuff. Who cares? Okay, that's something for professors to test you on. Okay, it's not much use for anything else because we don't even do it that way anymore. We put it into the computer, and the computer does a linear approximation of a bunch of little elements, right? So you don't even use Bessel functions anymore. But yes, it is a Bessel function. So if you now want to know how to solve Bessel functions in your head, you basically say, well, is it thick, thin, or mixed? And is it divergent or convergent? And it's going to be either one side or the other of this. And it's going to be like a 10% difference. Do I care about 10%? I probably don't know the thermal diffusivity within 10% of most of my materials. Okay? So who cares? So, in what cases does it apply? Basically, it applies in all cases. Now, I've had some of my doctoral students argue with me about whether, when I do these little problems like the heat effective zone size, whether I should have a factor of 2 in here. Well, what I solved for you over here was for the Fourier number equal to 1. And I just said that it's at 3 millimeter distance in a piece of steel at that particular travel speed of 1 centimeter squared per second with a 1 centimeter long well pool, I would be down, I would have dropped my temperature by 90%. Well, 90% is not my heat effective zone size. Well, about maybe 50% of the heat is my heat effective zone size. So yes, in fact, maybe I should have had a 0.5 here. And I've had some of my doctoral students argue with me for several years over whether I should put a factor of 2 in there. And I tried to explain to them, I don't care about a factor of 2. I really don't care about a factor of 2. You give me my paycheck, I might care about a factor of 2. But talking about heat flow to solve an engineering problem, I don't care about a factor of 2. I want to be within the ballpark order of magnitude. Now, if I need to be within a factor of 2, you can't use the Fourier number. You got to solve Fourier's second law, and that's when you give it to a graduate student and say, go solve this in the computer. And you can do that. There's plenty of people who do it. Now we have canned programs that can do this. But the thing is, can you solve the problem in your head and get the correct answer? And 95% of the time, you can do the simple Fourier number in your head and impress your friends. And believe me, I've done it a lot of times. I sit in some meeting with a bunch of engineers and they're arguing about some heat flow problem or some mass flow problem, and I just kind of sit there and say, oh, well, you know, we're off by an order of magnitude. Okay? And I'm basically taking the square root of 1. You know, I'm multiplying 1, dividing by 1, taking the square root of 1 in my head. They say, how'd you calculate that? I said, well, I just did it in my head. Oh, he said my heat professors are really smart, aren't they? If you don't tell them the secret, it appears that you are. Believe me, it works. Most of the time. So there's lots of different types of problems. It takes a little bit of experience. And let me say that after 15 or 20 years of doing this, I now actually can solve these types of problems in my head too. In fact, let me give you an example right now. There is a situation that I'm dealing with where they have these great big, I'll just call them 16-inch diameter steel cylinders. And the test block is what they call a 5-inch equivalent round. It turns out it's 4 inches by 4 inches by 8 inches long. So they make this casting of this great big cylinder, 16 inches in diameter. And since they can't cut this up, this is the part we want to use. They have this 4-inch square test block, so they cast the same tube in the same mold. This is just off one of the runner screws. Some of the metal goes in. You have a connection between a liquid connection or a pipe in between. You cut this off, and you can take all your tensile specimens, your Sharpies, or whatever you want out of the test block. And you go to the American Bureau of Shipping Rules. It tells you you can use this. Okay, so they cast these things, and then they have to heat treat these things to they call normalize the steel structure. So this casting shop puts these in the furnace for 4 hours. Puts this one in the furnace for 4 hours, puts this one in the furnace for 4 hours. The question is that an adequate amount of time? Well, it's steel, so I have a distance here of 2 inches that I'm interested in. I have a distance here of 8 inches. Right? 2 inches is 5 centimeters, right? So 4 hours is 12,000 seconds. So I've got 5 centimeters equals, is it greater than or less than 0.1 centimeters squared per second times 12,000 seconds or something. Is that 12,000 is 4 times 3,600 is 13,000 something, right? 13,200 seconds, is that right? 144,000 seconds? I mean, 14,400 seconds, there you go. 14,400 seconds. So, I now have 1440, I gotta take the square root of that, and I guarantee you the square root of 1440 is a lot larger than 5, or 20, you know, if you want, I can square the whole thing. This is 25 and this is 38. 12 times 38? 38. Okay. Well, yeah. 38. Okay, so 38. So 5 and 38. The 4A number is 5 over 30. Let's see. It should be 38 over 5. Oh, wait a second. No, I'm over here. Yeah, okay. I'm sorry. I'm thick. Okay, it's 5/38. I'm thick. I'm basically, this thing is relatively thin compared to this, okay? So I got a 4A number of 5/38, which is 0.12. I've got something like this. The center of this gets up to temperature in 4 hours. Okay? Now if I go over here to 16 inches, 2.5 times 16 is 30, right? Yep, something. 32. So I got square root of 0.1 times 32 centimeters. If I got all that right. That's, and what's that? Oh, so this is 32 over here. 32, and I got the same 14,400. Okay. So that's 32 over 38. 32 over 38. Well, that's not all that far from 1, which means the very center is barely getting to 10% of the temperature that I want. I want 1600 degrees Fahrenheit. That means the center is getting to maybe 200 degrees Fahrenheit during this heat treatment. So do you think they properly heat treated this thing? No. But they said they did. The steel mill, the heat treater says, oh, we did tests on our furnace, and we found that if you put these into the furnace, and we look at the thermocouples in the furnace, it only takes 3 hours for it to come back up to temperature. Well, have you ever put a cake in the oven? And you got to cook it for 30 minutes? And you open the oven door at 350 degrees, and you put the cake in, and it takes another 5 minutes for the oven to come back up to temperature. Does that mean the cake is done in 5 minutes? Don't think so. Okay? What they mean is the temperature came back, the furnace came back up to that temperature. That doesn't mean the part in the furnace came up to that temperature. Let me tell you, this is a real multi-million-dollar contract in industry. And these are the rocket scientists who are doing this. The properties in the steel are abysmal. Okay?
Where did the 5 centimeters come from again?
The 5 centimeters is 2 inches. I'm trying to find the distance.
Okay.
It's only half the distance of the 4-inch square, right?
So you need to use centimeters.
Okay. And here it's 8 inches. I'm sorry, you know, I just did this thing wrong. It's 8 inches. I did 16 inches here. So it's 8 inches, so that's 16 over 38 or something. Okay, well, in doing all this, maybe it's not 200 degrees, maybe it only got to 400 degrees. But given the fact that if I don't get up to 1200 degrees, I still haven't done something. In fact, what I've done is I've done temper embrittlement. And that's exactly what happens to these things. Okay? So, I hadn't prepared that. But you actually can do those things in your head. Sometimes I scratch them out on a piece of paper when people aren't looking. Okay? But you can do these things in your head. Okay? So now you know how to do at least 3 of your homework problems.
It doesn't even look like you need to do the numbers. You should just know by looking at it.
Well, I knew that. But I have to prove it to people. You have to be quantitative.
They should have known that.
Look.
It's like the difference between sticking a half-inch steak in a grill and a turkey.
Exactly. In fact, that was my original thing. In fact, if you go to one of the classic books on heat transfer, something called Bird, Stewart, and Lightfoot. Anybody study out of Bird, Stewart, and Lightfoot? One of you, okay? One of the problems in Bird, Stewart, and Lightfoot is cooking a turkey. Okay, and they ask you to calculate you know, the time it takes to cook the turkey. Now, they're doing it by fancy graphs and things like that, but nonetheless, it's the same thing. When I heard that he treated these things for 4 hours, I said, what? This is a 16-inch piece. The rule in industry is 1 hour per inch of thickness. Okay, so that would have said 16 hours to heat this thing, except it's convergent heat flow, so maybe it's only 10 hours. Well, guess what? They now are heating these things for 10 hours after having done lots of studies. Okay, but they never bothered to go through the heat transfer analysis. They basically cut up samples and measured properties, and they found 10 hours they got better properties on heat treatment than they did with 4 hours. Surprise, surprise. You know.
Question. How can you assume that the Fourier number is always going to be equal to 1?
Oh, that's what my student argued with me. Is it equal to a half? Oh, I'm actually over here. Assuming it's 1.
Yes.
Actually, I'm really doing greater than or less than. At this point, I want to know. I actually know two. I know all 3 parameters here, right? I know x, alpha, and t. So what I want to know at that point, the question is, am I thick, thin, or in between? Okay. So I just want to know, is x greater than square root of alpha t or less than square root of alpha t?
Okay.
So in some cases, like calculating a heat affected zone, I said, okay, let's assume the Fourier number is 1, and I know 2 of my parameters. Okay? I know time and I know alpha, and I calculate x, which is the width of the heat affected zone, which is what I wanted to know. In many of these other cases, I know x, alpha, and t, and I want to know, am I thick, thin, or intermediate? And so that's basically a greater than or less than question, right? And I realized part of the problem is I've been doing this so long, it's hard for me to go back. The fundamentals, maybe someday I'll go back but yeah, if you practice with this, and you start saying, well, I know this parameter, I know that parameter, and like I say, sometimes you know all 3, like heat treating these things. You know all 3, but the question is, did the heat get all the way in? Is it thick or thin? And for the 4x4x8 test block, it's thick. For the 16-inch round, it's thin. And obviously, I ended up, if these are roast beef, I came out with rare roast beef on the 16-inch steamship round, and the filet mignon, or the Chateaubriand I put in, is done to a crisp, right? Because I put them in the oven at the same time, for the same amount of time, okay?
Can you really, in fact, I mean, the whole purpose of doing this is to get a test block, right? It has the same properties. And
Right.
You can really have the same properties.
Oh, well, all you had to do is,
Yeah, cool.
you calculate the same Fourier number for the test block and heat treat it for a certain time, then heat treat this with the same Fourier number.
No, I'm not talking about the heat treat. I'm talking about, I mean, going back, just the basic casting to get different properties, isn't it?
Oh, yes, yes.
Because of cooling
And in fact, what they're supposed to do, but they got a waiver from the Nostra Veritas, okay? They were supposed to measure the properties on this, and then they were supposed to take one of these guys and cut it up and see if they correlated. But that was going to cost money, so they asked for a waiver and they got it. Okay? Okay, that's enough for today.